Okay, so we've just learned that that you can that we can define the dot product between two 4 vectors in this way. It's it's the product of the two time components minus the product of the two x components minus the product of the two y components minus the product of the two z components. And since this is actually definition, we just we should give it 3 lines. It's defined this way. And furthermore, we also define the dot product, or this, what follows from this is that the dot product between a 4 vector and itself is equal to this, which is the invariant interval. Sometimes we'll refer to, because of this, sometimes we will refer to delta S squared, the invariant interval, as the magnitude of a particular 4 vector or its length. Okay, some other important properties of 4 vectors are written down here. A 4 vector which is multiplied by a scalar quantity is another 4 vector. So a 4 vector which is multiplied or divided by a scalar is another 4 vector. And a 4 vector which is multiplied or divided by a non-scalar quantity is not a 4 vector. Okay, so now we're going to discuss a particular another particular 4 vector which is important in special relativity, and that's the 4 velocity. So the usual or classical velocity in normal three-dimensional space is defined as the limit of a displacement, a spatial displacement in time. For example, something moving from R1 to R2, the distance between them in normal space is delta R. And if that takes delta t, a time delta t, then as delta t goes to 0, then that defines our instantaneous velocity u. Okay, we can write this in differential form as shown here. Now we would like to find some analogous 4 vector to the velocity in space-time, but we can't just do the same thing that we did here. We can't define the 4 velocity as the limit as delta t goes to 0 of the as the 4 vector, okay, the 4 displacement delta x divided by delta t, because delta t is not a scalar, and so when we divide by delta t, we're not going to get a 4 vector, right? So a 4 vector multiplied or divided by a non-scalar is not a 4 vector. Okay, but we can divide by the proper time. Remember, the proper time is a scalar, right? We even said that, we even listed that on the previous view graph. Right? An example of a scalar is the proper time between two events. Okay, so the proper time is a scalar, so we can define by that, and that has units of time. Okay, so we can define the 4 velocity as the limit as the proper time goes to 0. Delta t is the proper time. Okay, as the proper time goes to 0 of the 4 displacement divided by the proper time. Oh, okay. So now plugging in the expression for the 4 displacement and using differential form, we find that the 4 velocity is equal to the derivative of the 4 displacement in proper time, which is equal to c times the derivative of time with respect to proper time, derivative of x with respect to proper time, the derivative of y with respect to proper time, derivative of z with respect to proper time, and these are all the components of the 4 vector. Okay, so now if you take into account that the basically this definition of time dilation, okay, that the time interval in any frame which is moving with respect to the proper frame is time dilated, okay, by the Lorentz factor gamma, then finally we get this expression for the 4 velocity. It's equal to gamma c, gamma ux, gamma ui, gamma uz, or sometimes in shorthand notation gamma c and then gamma u, where u is basically understood to be the velocity, the 3 velocity. Okay, so that's the definition of 4 velocity.